Alright, so let's go through trial example 1, 2017 H2 physics question. So electrons are accelerated in a vacuum right, before passing through a graphite film. So graphite film just means your carbon, as illustrated in the figure, right? So the electrons are then incident on the fluorescent screen. Concentric rings of light are being observed on the screen. Explain why electrons actually produce concentric rings right after passing through the graphite film. Okay, so first you look at the setup, right? So apparently there's a cathode. So cathode just means like a metal, right? So this is a metal, right? So notice one thing, you see there's a battery. Let's just say there's a battery here of 6 volts. This is actually to produce your electrons. So apparently, right, the current is going to flow. Eventually, the cathode get hot enough. So when the cathode get hot enough, electrons will be emitted. This process is what we call the thermionic emission. So of course in turn it's going to get accelerated, because as you get emitted, the electrons get emitted from the cathode, right, the speed will be rather low. So you need to accelerate through a potential difference. So you accelerate through a potential difference, then after that, as you hit the graphite film, right, it's going to get diffracted. So diffracted, of course, eventually you'll see all the concentric rings, right, on the fluorescent screen. So let's look at how do we explain. So explain why the electrons produce concentric rings after passing through the film, right? Okay, very simple. First, electron behave like wave, and as it encounters the film, right, it will get diffracted. So of course you can also talk about the interference. For example, you can talk about the constructive interference and destructive interference. Okay, for part B, the PD between the anode and cathode is increased, meaning the delta V increase, right? This actually increases the brightness of the ring. State and explain another effect of this change, right, in the PD on the pattern observed on the screen. Okay, so the other effect will be that, okay, for example, right, remember if you increase the potential difference, this will actually lead to a greater kinetic energy of the electron. Because why? Because Q delta V. So K is equal to Q delta V. So delta V increases, K increases, meaning that your momentum increase. Means that lambda equal to H over momentum, right? So momentum increase means that the d Broglie wavelength of your electron actually decreases. So when d Broglie wavelength decreases, right, you behave less like a wave. Means that you actually diffract less. So that is the effect. So the first state, right, so you just say, the diameter of ring decreases. Why is that so? So you just say less diffraction. Why is that so? Because as delta V increases, this lead to greater kinetic energy of the electron. So when the kinetic energy of electron is greater, right, so this actually mean that the momentum is greater. So based on the d Broglie wavelength formula, right, so lambda equal to H over momentum. As momentum increase, your d Broglie wavelength decreases. Hence, it will actually diffract less as it behave lesser like a wave. So just remember, for d Broglie wavelength, if your d Broglie wavelength is high, means that you actually behave more like a wave. If your d Broglie wavelength is low, like us, right, we behave more like a particle. Yep. Okay, so that's for part B. Okay, let's move on to our last part, the calculation. The electrons are accelerated from rest, right, through a PD of about 1200 volts. Calculate what is the d Broglie wavelength of the accelerated electrons. Okay, so imagine I got a battery, so 1200 volts. So electrons right here, right, doesn't have any K, because they say it's from rest. So meaning that the V is equal to 0, meaning that your kinetic energy is 0. So what energy does it possess at this point, right, is that it possesses high electric potential energy. So just before you hit the positive plate, so this second location, right, all the EPE is being converted to your K. Means that at this point, right, your K will be high. So you can see the EP is being converted to your kinetic energy. And how do we actually calculate the kinetic energy? Very simple. So you just use this formula. So Q delta V. So delta V is about 1/200. Q is about 1.6 times 10 negative 19. So you do the calculation of your kinetic energy is about... Okay, so the kinetic energy is about 1.92 times 10 negative 16 joules. Okay, so now we are asked to determine the lambda, right? De Broglie wavelength. So just go back to a formula. Lambda is equal to h over p. So I know what is my h. My h is the Planck constant, but I do not know what is the momentum of the electron. But I got the kinetic energy. So you just need to relate back to the kinetic energy and the momentum relationship. The relationship is as such. So kinetic energy is equal to p squared over 2m. So I got kinetic energy calculated. I also know the mass of the electron, right, is about 9.11 times 10 negative 31. So in turn, I can calculate what's my p square. So to do the calculation of p square, you simply just multiply 1.92 times 10 negative 16, right? You multiply by 2m. So this will give me about 3.4. So the p square, right, is about 3.49824 times 10 negative 46. So you just simply just square root. So square root 3.49824 times 10 to the power negative 46. So this will give me a momentum of 1.87035824 times 10 negative 23. Then the last step is to calculate the de Broglie wavelength using lambda divided by, lambda equal to h over momentum. So do the substituting in. So Planck constant divided by the momentum. 0.35824 times 10 to the power negative 3. So this will give you a de Broglie wavelength of about 3.54 times 10 to the power negative 11 meter. So that is how we do the calculation for the de Broglie wavelength of your electron.